right, let's do this. 9:58. Oh, more people coming in. I don't want to be saying this stuff all over again. All right, let's talk about data centers today. Data center high performance compute challenges and solutions. So we're going to give you an overview. I'm going to give you an overview of what we're seeing out there today, objectively. So I am Mark Ivanko. I am principal engineer, CEO of Brunspack. And as I indicated to some of you folks, I've been doing this this is my 44th year. Data centers, right? So we've done about 6,000 of these things over the years globally. Consult, design, build, commission. What are my options? What are my alternatives? So my intent today is to give you what we're seeing in high performance compute. What are people doing in projects? And I added a section, let's see here. This is our agenda of what we're going to go through today. And I'm going to take my time so people can get a feel of what the trends are that we're seeing. I did add a section 6 before questions and answers. So when I was flying down last night, I did put together 6 project examples of high performance compute. What are we seeing? How are we seeing it? What's coming out? What are the customers doing? What's their concerns? Why are they doing these things? So I'm going to go over that, if I can see it, as soon as we're done. So today we're going to go through Data Center High Performance Challenge. What is it in 2023? We're going to talk about the 19 elements. What are the 19 elements? What does that mean to a data center and high performance compute? The current data center activities surrounding HPC, what are we seeing globally? What are the consultants doing? What are the design engineers doing? What are the builders doing? How are they trying to get ahead of this? We're going to talk about the results of some of this 2023. And it's really positioned some of the folks, and by the way, I'm a big Disney fan. Do we have any Disney folks here? The analytics of what Disney goes through is kind of impressive, needless to say, on where you are, what how they're charging you. We're going to talk about that in a bit. So we're going to talk about results of HPC deployments. We're going to talk about the conclusion. What are we concluding today? Oh, wait a second. See? I got to hit the button. All right, 5 minutes. No, actually, I hit the button right at 10 o'clock. Not bad. Anyhow, there's a button up here that tells you when to shut up and stuff. So you got to hit the button. And then we're going to talk about examples, some real-life examples of what's out there, what specific projects. I'm going to respect the NDAs that we have, but what are the specific projects and how are they handling this? What does it mean to them and why are they doing it? All right, let's go on. So let's talk about high-performance compute challenges and solutions. So as you can see here, and by the way, yeah, the pointer works. See that? Okay, good. The increased use of technologies, including the Internet of Things, artificial intelligence, machine learning, have created large demand for processing massive amounts of data at a faster rate. This is just a given, right? The result is high-performance compute clusters being deployed to solve the problem. So the densities that we're seeing has been significant. Look at the HPC power density per cabinet. These are real-life examples that we're seeing today. This is enough to roll your socks down. 40 to 100 kilowatts per cabinet. Think about that for a second. That's some high-power solutions. And most all data centers, whether it's enterprise, whether it's co-location, whether it's cloud, are not suited for this at all. So it's something that we have to really look at. So the HP solution, it consists of compute, network, storage, and here's the key. And where's Mike? Is that you, Mike, over there? Anyhow, I want to clarify, there's 2 major divisions of high-performance compute, if you would. There's high-performance compute research, which has a higher tolerability of going down. They just need the front-end nodes protected, a little bit of UPS, not generator-backed. That's research. However, there's high performance. The other is high-performance compute production environment. That's for these enterprises that are running tier 1 applications. They are critical. So keep this in the back of your mind. Typically, in high-performance compute research, right, it does not require the same reliability, physical facility infrastructure reliability, that the other tier 1 applications. So what does that mean? It means that I could have a deployment of 10 90 kilowatt per cabinet racks. I'll give you that example. 900 kilowatts over 10 racks. But by the way, only needs 50 kVA of UPS power. Doesn't need any generator back power. And the cooling is N because it can go away, that research. That's high performance compute research. However, in that same application, in a tier 1 application for a production environment, it is incredible. You're putting 10 racks, 900 kW of UPS power, redundant, 2N configuration. It's 1.7, 1.6 total power to a 2,500 square foot area. That's a whole different ballgame. So typically though, if you go high performance compute research, what we're finding in general, people are trying to retrofit their existing data centers with high performance compute. And by the way, you're going to have various densities and various reliabilities coming out. Hey, Tad, wave to the camera. Look at the camera. He's got a lot of money. This one's got a lot of money. I shouldn't say that, he does. Go on, Tad, wave your hand. I'd be remiss if I didn't say these things. All right, let's talk about high performance. But what enterprises does this go through? It goes through everything. Research. By the way, these high performance compute research are basically driven by grants. These universities are getting multi-millions of dollars from NIH, from the government, to do this high performance. That's what's part of it. We were just part of a grant where it was $100 million they were getting. And the data center part for high performance compute was only $15 million to retrofit. But they're getting $100 million over 3 years. So these research scientists are like rock stars. Energy, aerospace, weather, right? You remember it used to be the weathermen say all kinds of whopper stories? You don't have to do that anymore because the data that they're getting is real time coming through everything. Automotive. By the way, automotive, we did a study, and this is part and parcel, a 5G edge study. Why? Edge compute, automotive, why? You know how your cars are going to be so-called intelligent? I can't wait for this to really happen, right? Intelligent and driverless. Well, guess what? You want your data processing at the edge. You don't want your data in New York City going to Los Angeles when it's telling you to shut their brakes on and then coming back and there's a latency issue. So this is all high performance. It's getting higher and higher density for the edge compute. Pharmaceuticals, real estate, medical. So when you think about this, and by the way, think about this in the context of AI, right? Artificial intelligence, and this being able to predict everything, right? That's why there is a real concern about what's going to be deployed. There has to be guidelines on this because there could be the criminal element that works on this as well. Retail, banking, financial, traffic patterns, right? So you can see throughout, you have a whole bunch of marketing, predictive analytics, military, as I gave you that example out in Seattle. There was another one done by a major banking institution. I thought this was fascinating, where basically they concluded that they needed about 1/4 of the physical facilities in banks in the future. That's it. And by the way, everything will be mobile, right? But by the way, what they're concerned about, and they can tell, by the way, when you're walking on a street past a bank, how you react if you're a candidate to open up that type of checking account. So this is real life type of stuff for them making money. Let's talk about section 2, the overall data center 19 elements and the compatibility. So what we're saying is this. This is what we've come across now is that when you come up with a high performance compute solution, we believe there's 19 elements for you folks to consider. Now understand, these are technical components, right? And I'll go through each one of them, but we start with the facility infrastructure. What part enterprise? What's the energy efficiency associated with this? And we're going to talk about ESG and carbon footprint reduction. But what about my compute hardware? So, and look at that, there's high performance compute. These are all elements you just don't knee-jerk for a high performance compute data center. So all these technical components, the compute hardware, am I going high performance compute? Am I staying legacy? What am I doing with my applications? Are they tier 0, tier 1? Right? Because then we talk about how does cloud play? And cloud's got a great role for this, for parts of these solutions. What about disaster recovery? Am I going to have synchronous data replication of my tier 1 applications in high performance compute? If that's the case, I can go with an N type of data center. Then we talk about co-location. Are there candidates, tier 3, 4, for co-location? Sure there is. There's ideal candidates for them. Then you talk about migration relocation. What's the impact for you to migrate and relocate? So think about this. I'm going to continue through these 19 elements, but the point is, this is what your board wants to look at. Your trustees. What's the total cost of ownership versus best practice versus risk? That's really what it's coming down to. So I have to think, what about my migration relocation? What about my software? The hospital folks, if I'm running patient care, and by the way, I don't have synchronous data replication, that means I'm in deep sneakers. I talk to my neighbors, the doctors. If they go to your bed, right, and they used to have the charts on the end of your body, now they have the computers there, right? If that network goes down, you got problems. You could be in deep sneakers, right? They don't know whether they gave you a horse pill or an elephant pill before, and now they're going to have to try to treat you if you run into problems. So this is really real life type of situation. The modularity, scalability, flexibility is dominating right now. If you're not there, you better be there, even with your enterprise data center or your cloud, because they're coming after energy, and they're coming after energy big time. And they're going to put some new metrics associated with that. Your network, by the way, and I learned this in law school, it was never stealing. The word they used was permanently borrowing. That's what we taught. You don't steal anything, somebody permanently borrows that. That's how they say it in law school. Anyhow, the point is this: what about your network? What about your data? Who is securing your data? Who's liable for the data? Then we talk about number 11, service level agreements. Do you have them? Is there any fine if you go down? Is there any government regulations with that? Your personnel? How about CapEx versus OpEx? This is another key thing. Here's another trend, ladies and gents. For the colo guys, the cloud guys, right, 2008, when it was an OpEx cost, I could spend $200,000 a month instead of spending 20 million capital dollars, right? It's a no-brainer. I'm going. Here's a news flash. You can have your own OpEx costs. If it's projected to be $20 million in facilities, there's financing people that will come in and lace it to you right there for 30 years, and you don't have to go anywhere. You've just eliminated migration, relocation, network relocation, everything down the line. So this is something big now, because they're actually financing you in place. We talk about containers. Are containers applicable? Guess what? I'm going to give you an example later on. I think it's number 6. A container, high-performance compute. They were not going to go through the retrofit of their existing data center. I think it's about 2,500 square feet, 900 kW of UPS power for it. Unbelievable, because the container was conducive to them. Then we talk about the government, corporate. By the way, government is going to get more involved with this, with the ESG as we continue to go on. Cybersecurity. Oh, wait, legal repercussions. Tremendous. Tremendous. It's building. The legal beagles, because what happens if I shut down Delta Airlines in Atlanta? Who's going to pay for that? Is it a vendor? Right? You now have the ability to really take down somebody big time. By the way, in some of this high-performance compute research contracts, there's language that says you will maintain 99.9% uptime, right? And have synchronous data replication. So you have to really watch the legal, because otherwise there's fines of multi-millions of dollars some case. Compliance, edge computing. So edge computing is coming out there, right? And compliance is going to be changing, but edge computing is another major impact to high-performance compute, right? They're predicting that it's going to impact the cloud to the extent of bringing process to the edge as soon as possible to reduce latency, reduce the cost. So, having said this, the summary for this is the board wants to know what's the total cost of ownership versus best practice versus risk. Don't come in to me with a vendor solution. Don't come in and tell me I'm building this enterprise data center for $25 million and I didn't look at all these other elements. What part cloud, what part co-location, what part enterprise? How are you going to address that issue with Gartner that's coming up, where they say 75% of the companies that don't address AI and that data in the future in 5 years will be out of business? Now, maybe they're right, maybe they're wrong. They're pretty smart people. So this is a total cost of ownership versus best practice versus risk. But it's coming. Even me, I'm cheap, right? Very cheap. Walmart, anyhow, I don't know if the Walmart got here when we consulted with them, but anyhow, so I go and buy the open bags of popcorn in Walmart, right? That's what it is, because I get 50% off. So if a bag's open, I get 50%. It's a little stale, but that's okay. For 50 cents off, I can do it. What's amazing, they now have me track on my car that I'll get a pop-up and say, Mark, you must have ate that bag of popcorn by now. It's a week later. Why don't you come in and get a full bag? So they actually know my information about what I bought, right, when I went and scanned through and paid for it. Absolutely fascinating. And if you ever notice preventive maintenance with the doctors and the pharmacies, and they're calling you, right? It's about revenue generation. So the key is total cost of ownership versus best practice versus risk. Don't just knee-jerk for high-performance compute. All right, let's talk about this. Here's the key. What we're finding is that in high-performance compute research, right? Research, the existing facilities are not conducive in general to handle these sort of densities and loads. They're not. So therefore, what you have is you might have high-performance compute research with an N configuration, a need, right? That's all. I'm okay if it goes down, but my rest of the data center is a production tier 1, 2N configuration. How do I manage that? How do I retrofit that? That's high-performance compute research, and vice versa. You might be in a production environment, whether it's cloud or co-location, and then with tier 1 applications, but they might only be 6 or 7 kW per cabinet, or 10 kW per cabinet. What happens when I come in with 50 or 60 or 80 kW per cabinet? Here's the other thing. By the way, high-performance compute, we're not even done interviewing the IT people. It's got to be modular. They might have an initial configuration with Lenovo at 40 kW, but what's the vision? It's got to be able to scale, right, to 100 kW. And the last thing you want to do is say, well, you said 40 kW, they come in with another grand at 60, you can't handle it. And then you have to call your brother-in-law in with the chewing tobacco and the welding rod and the blowtorch, and he's in there trying to retrofit. And you don't want to do that. That's not a career builder, although you can do fishing and bowling, right, like you like to do, John, right? You could do that as another career, but you don't want to be doing that. And by the way, we are actually seeing now deployments of over 100 kW per cabinet being forecasted in the next 2 years. And separate high-performance compute facility from production environment, you know what some folks are doing? Get me away from my data center. Get me away from cloud, get me away from co-location, give me a container, give me a modular approach, because the amount of retrofit is not worth it. I want something custom that can really go there. Not custom, you can actually bid it to multiple manufacturers, but they're actually, and by the way, the footprints are this, and the densities are like this. It's incredible, the amount of power that they're taking. Let's go to our section 3. We're doing good. Can somebody turn the heat up here, please? I just want to like sweat to complete death. Can we do that? Anyhow, Lord love a duck. I mean, we're all engineers, and this is a classic engineer. We can't get the air conditioning right. Anyhow, and by the way, us engineers never make mistakes. I learned that in undergraduate school. It's only the information we get is wrong. I had to defend ourselves. All right, let's talk about current data center activities surrounding HPC. What's going on out there? What's happening? Number one, the process is to understand the end user client, short, long-term, high performance compute mission and corresponding rack KW load densities. This is key. Information technology folks start thinking about they have a plan. Is it really critical applications like in hospitals or banks or something that would be devastating to lose? Or is this type of data something that could go away? If it goes away, the data center goes down. That's critical. That's step number one. Number two is understand the end user client compute uptime requirements. This is key. What is their uptime requirements? And by the way, short and long term. Is it really to grow beyond belief? Is it really that if this, by the way, if this data center goes down, it takes our company out of business? Which I couldn't believe. I actually saw that happen, and you see it's public. I'm not stating anything, but when you see these public events happen that take down entire enterprises, it's amazing. So you want to know what do they need protection on their front-end nodes or their general processing. And then ultimately, translate the HPC short, long-term KW rack vertical demand to understand the immediate versus long-term electrical mechanical impact to the data center floor space. a classic example, we just got done discussing with a utility company and said, hey, by the way, yes, we need 2 megawatts right now for an initial high-performance compute installation pod, but we reserved 10 megawatts. So we have a 13-2 line that can actually drive 10 megawatts, actually 2 of them, right? So we're actually cutting down to 2 megawatts now because we know in the future it's going to be unbelievable. Unbelievable. And so, but just having some forethought with that, they can bring in the lines, they can size the capacity, then they can work with their substations about what, how to go and deliver that. Identify short, long-term mechanical thermodynamic impact options of HPC. So thermodynamics, near and dear to my heart. I was tortured in that one. I still have flashbacks to thermodynamics. Carnot cycle, anybody with Carnot cycle? What a waste. I can't believe they taught us that. 100% efficient cycle? And this is back 197 years ago in undergraduate school. But anyhow, thermodynamics is relevant now. We're not bad people. I tell my wife, we're not bad people. We're just misunderstood. Thermodynamics is key. Thermodynamics is key. Why? Because it's going to tell you, it's going to show you how far can I go airside load? 20 kW per cabinet? When does containment come into play? When does rear door heat exchangers, when I start pushing over 25, 30 kilowatts per cabinet, by the way, I need rear door heat exchangers, in-row cooling, that can bring me up to the thresholds of 60 to 70 kilowatts per cabinet. And then, by the way, when I'm at 100, it's to the chip cooling. To the chip cooling, if you can imagine that, right? And now, with immersion cooling, I'm going to give you, that's example number 7, I'm going to give you in a little bit, about immersion cooling. And what does that mean? And by the way, immersion cooling, their representation right now, right, we haven't proved it, 250 kilowatts per cabinet. 250 kilowatts per cabinet. You got to be kidding me. I don't know if they smoke dope, but who knows? Anyhow, 5. Let's talk about 5. Confirm compute hardware manufacturers' warranties associated with the chip cooling and immersion cooling. By the way, warning, caution, right? When you start playing around with the manufacturer, whether it's IBM, whether it's Dell, whether it's Lenovo, whether it's HPE, you have to make sure your warranties are still in place, right? Little minor detail. Because if they say you touch my cabinet and you bring to the chip cooling, I'm not warranting that, you don't want to go down that path. And this is a battle that's going on right now. And develop a short, long-term data center facility, a MEP modular strategy to scale with HPC. What are we saying? As IT grows, the facility infrastructure should grow. Modular, scalable, flexible. Example, IBM iCloud, 5U server, right? 21 kW, that's a 5U server. 21 kW and 5U. And a 48U configuration. If I deploy 3 or 4 of them, I'm up at 60, 80 kilowatts in a 48U. How is your mechanical systems reacting to that? How are they scaling with that? That's a fascinating thing. And by the way, it's neat because you can utilize DCIM. You can go and have variable frequency drives come up. You can go and sit there and increase your in-row cooling on your rear door heat exchangers because you have layered mechanical systems that can increase. That's cool stuff that you can do right up front. And the initial cost of deployment versus return on investment is critical. This is long term. These are what these companies are going for right now, and they're doing it pretty well. Really, I do want the heat turned up to at least another 20 degrees. This is crazy. Anyhow, let's talk about the results of HPC deployments. What are the results that are happening? Tremendous speed of processing results. It's incredible. I always joked, I remember doing, what was that college board? Remember you used to take the college board? I forget what they named it. They were out of Princeton, and you took the SATs, and you'd wait by your mailbox for 3 weeks to figure out that you're not going to Harvard. You had to wait 3 weeks to get notified you're not going to Harvard. Well, the good news is, now they're processing your data. You know when you're walking out you're not going to Harvard. How's that? So it's a lot of relief. It's a lot of stress off you. You don't have to worry about this or talk to your parents. Well, what if? You know you're not going to Harvard. I told that to the Harvard people when we were consulted. They said, Mark, don't talk about those things. But anyhow, because you talk about admissions and they get all hairy and stuff. That's a whole nother story. Data center facility improvements are deployed to accommodate modular, scalable, flexible, reliable HPC deployment. So don't get hung up on, I'm going to my IT guys and they're going to give me, he, she, whatever it is, that we're going to go and sit there and say 20 kW per cabinet. It's got to scale. You have to have a vision because it's not backing off. Many end user HPC applications do not require tier 3, 4 AMEP superstructures. Now again, high performance compute research. That's different from high performance compute. If it's in a production environment, yes, the AMEP will be at that reliability, or could be. So that's a key thing to look at. Large data center real estate consolidation results realized by deployment of HPC loads from legacy to less dense loads. We're seeing that the consolidation of some of these legacy applications that are really happening, not only virtualized, but now they're really going into these high performance compute arrays. Incredible. Incredible, the processing power. So this is the results of what you're seeing. HPC is delivering real-time AI to the client community. Results in increased profits, market share, revenue, and marketing visibility. It is amazing. I mean, the amount of data that's being processed and that you're coming, it's making these companies money. They're not just doing this for fun. HPC is being designed from a mechanical standpoint to operate in higher inlet temperatures. By the way, ASHRAE 9.9, 80-degree inlet temperatures. Hey, what about 90-degree inlet temperatures? Hey, warning, warning, if we start going 90-degree with a delta T of 25 degrees, right? Watch out for your power cabling. Watch out for your network cabling, because some of them don't operate in those type of temperatures. So you have to think about that, right? Most of all compute manufacturers continue to deploy HPC now and in the future based on return on investment. 2023 HPC deployments at Brunsbach up to 100 kilowatts per cabinet. This is today. 100 kilowatts per cabinet today. A survey of CIO industry leaders found, there it is, 75% believe if their business does not address AI, HPC by 2025, they face bankruptcy. Can you believe that? Think about that. Does that make sense? Probably, maybe, right? I don't know, but it's really saying our market characteristics can be defined, right? Where you're going, how you're going, what you're going to pick up, what you're likely to buy. You know, I'm cheap. My wife doesn't go to Walmart with me and said nothing against Walmart, but anyhow, that's why I love that. Great buys for me, but she's going to higher end stores. So she gets the coupons electronically with the so-called discounts. Incredible. Yeah, I'm glad. Let's not go down that path either. We have a lot of opportunities to take this whole place right down. Talk religion, politics, sex, and then let's open it up to the marriage situation. All right. Let's see. And there's a survey that we talked about. And by the way, it's really real. It's getting more real. So let's talk about what the conclusion of today is. HPC deployments are growing at an exponential level. I've never seen the growth in my day. I thought the compute manufacturers, again, I'm not a Harvard graduate, I thought the compute manufacturers were going to back off, and that's not the case. The growth of HPC is based on increased use of technologies like Internet of Things, artificial intelligence, and machine learning. The initial rates of return of properly deployed HPC, look at this, is reporting less than 3 years. Is reporting. Think about that. Now, understand, there's two delineations of HPC, and I want to be clear. High performance compute research that maybe doesn't have all the uptime and availability, that can maybe go to a lesser tier N+1 type of configuration, versus high performance compute in a production environment, these major companies, by the way, those uptimes are through the roof. Think about the multi-millions of dollar differential between just that philosophy right there. Multi-millions, multi-millions. The industry served by HPC are exploding. And by the way, what I thought was fascinating, and it's probably true, you know who's destined to be replaced too from artificial intelligence? Paranoid, schizophrenic, conservative engineers. And by the way, I got that welded on my rear end at Lehigh because they destroyed me when I was there. That was the worst experience of my life. I won't go into that. But that's absolutely correct. Because think about it. If you can put in thermodynamics and airflow and come up with a solution that's vendor agnostic or vendor neutral, right? That can start bringing down, think about the millions of dollars that you don't have to go through. So engineers, architects, do I really have to design something? Can I put it in an analytic funnel and come up with some solutions? But think back to those 19 elements. Remember the 19 elements I was talking to you about? They are technical groups of the overall solution, right? And we technical people by nature are antisocial, right? We don't like people. We don't like to talk to people. You know who I'm talking about. You know, you have them in their mind. You're a network guy or you're a network girl or the hardware guy. You know, yeah. Anyhow, it was like a Mel Brooks. Mel Brooks is my hero. It was like a Mel Brooks movie when I was interviewing one of these Ivy League institutions for their high-performance compute. You couldn't make this up. But you have to talk to the network people. You have to talk to the hardware folks, the software folks, the facility folks to come up with a complete solution. Compute manufacturers, including IBM, Dell, HPE, Lenovo, will continue to develop high-powered compute racks. They're not backing off. Unbelievable. Unbelievable. They're saying you figured it out. So, and I'm going to give you some examples in a second. Cloud, co-location, edge, container, enterprise data center continue to evolve to address the optimal solutions. If you see it, they're scrambling. Some of these high-performance compute, they're not designed for it because think about it. Remember watts per square foot? And I'm preaching to the choir for some of you folks, right? 100 watts a square foot, 200 watts a square foot. Well, this isn't a watts per square foot discussion. This is densities where in 1,000 square feet, you're going to have over 2,000 watts per square foot, 3,000 watts per square foot. Unbelievable. But by the way, you might have adjacent applications based on the densities lower that are going to be 150, 200 watts per square foot. How are you optimizing your energy efficiency with that? How are you delivering that type of solution? So, before we go to questions and answers, I want to give you 7 examples, if I can read them. Number one, this was a university, right? High-performance compute research did not need the uptime requirements. Their initial high-performance compute was 30 to grow to 60 kilowatts per cabinet. It was retrofitting into an existing data center with their tier 1 applications. The thermodynamic principle showed in-row cooling. That was the optimal solution for them. In-row cooling that the mechanical systems can expand from 30 to 60 without getting your brother-in-law in there with the chewing tobacco and the blowtorch. By the way, it is not critical. The high-performance compute research was a grant of $25 million, and they can go down. So therefore, they only had an incremental 50 kVA of UPS power, no generator behind this. And by the way, they got the grant. Let me give you an example, number 2. Another research institution. They had an existing production data center, 5,000 square feet. This is the main jewels, right, of where everything was at. They had a mix between tier 1 and tier 4 applications in their data center. By the way, high-performance compute research grant, $35 million, $40 million. Here's an incredible thing. They have 3 lines of power, if you would. They have a 2N configuration on UPS and generator, that's line 1. They have a UPS generator-backed line 2, and then they have a street power, line 3. This could come off of line 3, doesn't need the incremental. Absolutely fascinating. They were awarded the grant. The CFD model, by the way, showed that the in-row coolers were the optimal, not the rear door heat exchangers. Let me give you another example. This is a production company, Fortune, let's just say under Fortune 20. I got to watch NDAs. Under 40, big, right? Big, gigantic production type of environment. They're running, they went from 4, 6, 10 kW to cabinet. Now they're running at upwards of 40 kilowatts per cabinet. They have an existing 45,000 square foot data center, aged, that's not ready for this. But this is one of their critical applications. We ran the CFD model and stuff, and what they came back with, rear door heat exchangers to retrofit. Why? Because the raised floor, again, this is an older data center, raised floor, thermodynamics, here we go. Q equals CIA. I know that's near and dear to your heart like it is to mine. Q, cubic feet per minute. C, coefficient of friction. I, velocity. A, area. That's how you get fluid flow, right? By the way, couldn't get it in the underfloor cavity. Why? What was in that 12-inch cavity? BX, Twin X, ex-employees, beer cans, all kinds of stuff. You couldn't get any air there. And by the way, here's the irony. Mel Brooks would have a field day of it. We had a customer saying, I've got 200 tons of cooling capacity redundant. I have a load of 80 tons, and I'm failing. They said, that's impossible. I said, no, it's not impossible. You have capacity. You don't have distribution. It's static pressure in CFM. So I said, and by the way, this isn't something easy to fix. So that's another example. Here's another one. a research institution. This is prefabricated container. They said, you know what? Our data centers are 20, 25 years old, some cloud, some co-location. They went to cloud to get the price. They went to co-location to get the price. What they found? A pod. A pod was suited for them. This is 10 racks at 90 kilowatts per cabinet to start. So 900 kilowatts of power. This is only in a 2,500 square foot pod. That's it. It's a container. 2,500 square foot with another 1,500 square foot for the power module. They found it cost effective, that's the easiest cost effective way to go and deploy it. Plus, they were able to drop the pod right where their network, where their substations were, and where their network connectivity was. Unbelievable. And by the way, high performance compute comes in a variety, right? 48U cabinet. You could deploy a couple U, 3, 5U in high performance compute, and it keeps on stacking. It's not just one box, right? It's multiples that come in there. So you start taking, you could start at 5 kW, 10 kW, and here's the other example I'm going to give you. Here's a hospital, high performance compute research. And this is a gigantic hospital. Their data center itself is about 5,000 square feet. By the way, they started deploying some of their high performance compute arrays, smaller arrays in the data center. Now all of a sudden, these hospitals, and there's probably 15 of them tied into this one data center, they said, we got to put this high performance compute. This is a tier 1 application, critical, 70 kilowatts per cabinet, over 12 cabinets, 840 kW that needs redundant UPS power, redundant chillers, redundant generators in a basement data center of a 20-story hospital complex. And by the way, HPC, they don't want to, we sit there and say, listen, this is going to be open heart surgery. This is going to be major, multi-millions to bring the facility infrastructure to it. The reason why they don't want to move is because they've already established their software in that room. They've already established their hardware configuration. The network hub is there. So for them, they don't care. So now you're going to try to shoehorn, think about this, 70 kW on 18 of these. I mean, 70, so the bottom line is, the feasibility study right now is showing that the cost for the facility infrastructure retrofit is in the $50 to $80 million range to start. Because you have to run, think about it, more towers up 20 stories, right? More chillers, more generators. And this is in the city, by the way. But again, you let them make a business decision. So, and then here's one for you. This is a pilot that we're working on right now under NDA. This is liquid immersion in the central part of the United States. Liquid immersion cooling, if you haven't heard about it, 250 kilowatts per cabinet that they represent, right? We have not seen it. We were selected as the guinea pig, as the expert, to go work with them because we said, hey, listen, we don't have experience in deploying that. They said, well, you've been around. You'll probably, if we hum a couple bars, you'll probably get it. I said, well, we're going to test it. We're going to make sure that we work with the manufacturers because this is significant. And by the way, this 10,000 square foot data center is only for high performance compute liquid immersion centers. So these racks, every rack is designed for 250 kW. We're in the feasibility study. Once we're out of NDA, we're going to probably announce some results on it. And then finally, an example that we had is that the critical part of this is this new ESG. Show of hands, how many people have seen ESG or heard about it? Hands? Okay. All right, you're still alive. I'm sweating to death, but you guys are still alive. All right. So ESG, right? Environmental, social governance. What are you doing for carbon footprint reduction? How are you doing that? What are you taking for energy conservation measures? By the way, these big power, right? Ashburn, Virginia, right? There's different states that are very conducive for power costs. We have one customer that negotiated with the utility company, the state, to get a charge of 2.5 cents per kilowatt hour for the next 45 years. And they brought their data center, their massive data center there. Think about that, right? But what's happening with water being restrained? It's going to be something that you're going to have to pay for, right? So how are you doing the cooling? How are you going to take the outside air? Like today, this is what? We're in Austin, Texas. Is that where we are? Are you sure? All right. You sound pretty fine. He's got more money than God, too, so I'll take his word for it. So we're in Austin, Texas. Why am I paying for cooling today in my data center? I'm going to guess it was 58 degrees Fahrenheit this morning, something like that. Why am I paying for that? Why am I taking the energy to pay for that? Why don't I utilize the outside ambient temperatures to go and take you can. Now, again, thermodynamics is going to tell you there's only a certain point where I get up to a threshold where I have to take water and take the heat out. But why can't I do that? You certainly can, right? And there's going to be more. And you're going to see more and more of these things coming. And by the way, people say, hey, I want to do solar panels. Yeah, you can do solar panels. But in general, the data centers far outweigh the demand, and they need continuous power. So you have thermal reserves. You have a whole bunch of different options that are out there, but they're coming significantly. And the manufacturers are getting pressured to operate in higher ambient temperatures. So if I go to 90-degree inlet temperature air, and my friends from Canada, do we have any Canadians here? Oh, all right. So you got igloos. They got massive igloos from coast to coast. So that's what I learned. Not being a history guy, but when I went from there, from Vancouver to Edmonton to Toronto to Winnipeg's got the bugs, dude. By the way, I don't know if you're from Winnipeg, but here's the point: they're freezing up there, but they're cold. Why wouldn't I utilize that outside ambient temperature? Take down. You talk about a PUE, right? Only drive my compute power. Drive that external air and utilize that and take away the power consumption I have. So ultimately, you're going to see more and more pressure with that. So, and the last thing I want to talk to you about is that what we're seeing as a trend is the reaction for penalizing some of the inefficient data centers that are out there, whether it's cloud, co-location, enterprise. They're starting to come up with metrics to say, you're not efficient. I don't care what you're going to pay. Now, this is going to cause, I think, a tremendous transformation in the whole data center industry, because it's going to say, if I deploy 5 kilowatts in a cabinet, I want that exact cooling for it. Don't need anything more. If it goes to 10, I get 10. Not, I got a 5 kilowatt cabinet, I'm using that as an example, and I'm providing 200 tons of cooling capacity in that room. What a waste of time. Right? What a waste of time. So you're going to see more and more tremendous strains on the environmental, social, governance type of issues, and we're addressing them now from a data center perspective, right? Not only people, but from a data center perspective. So that's around the world and back in data centers, and I think we got 9 minutes and 41 seconds based on the green box here. I'll take a couple questions right off the bat. All right, you had your hand up first. Okay.
And then another change in HPC is we run 483-phase to the rack.
There it is.
So it's changing. And that helps a lot.
No, so you can start saying so you're running 400 kilowatts per
It's per cabinet. It's HPE cheats, so they make their cabinets double wide.
Yep.
So it's a terminology change too. But so the cabinet's 400 kilowatts, 480 volts.
And you're going to see more and more of this out there. And our thing is, what we're doing, because if I didn't tell you, I'm a paranoid, schizophrenic, conservative engineer. Can I say that again? Because I was really wounded in undergraduate school. But anyhow, the point is this. We want to see it up, operating, serviced, and issues coming down the line. Other questions? You had a question.
As far as the new standards, as far as reuse of the heat, in the northern climates, that sounds like a great idea. Heat a pool, heat the parking lot, freezing over. In the south, Houston, it's summertime for 12 months.
Yeah.
Energy reuse of that heat exhausted from the data center. What ideas or experience have you seen or solutions for that?
Limited, number one. Number two is you actually have to have a demand, like a university had up in the northern part, had a dorm next to it that had a full year-round heating cycle required, but it was adjacent to it. In general, when we've done those studies, it was not cost-effective to go and recover the heat. Other questions? Yes?
What have you seen the trend driving HPC directly to the edge at that scale?
Yeah, we are starting to see more and more, but not to the extent of the 90 to 100 kW. We are seeing densities going to like 40 kW per cabinet to the edge. Good question. Edge computing getting up to 40 kW for the cabinet. Yes.
Are you seeing trends with backup applications in the application layer, reducing the requirements for facilities backup?
Yes, good. You must be. Are you a Harvard graduate? That might be a Harvard graduate. You're absolutely right. Because the point is, if I have synchronous data replication between my tier 1 applications, I don't need this robust facility infrastructure. I can get away with N, and maybe N plus 1 max on one and N on the other one. Absolutely. That goes into that total cost of ownership versus best practice versus risk. Absolutely correct. That's a key point. Yes?
That liquid cooling project pilot, what's the number one feasibility thing you're trying to check on?
Well, our initial reaction, the question is on this feasibility that we're doing right now is what's the number one concern that we have? We want to make sure that the manufacturer's warranty, because some of our customers, and they have big data centers. The compute hardware is enough to roll your socks down. If you think facilities cost is right, one of our customers had like, I would say about 300 times 2, so $750 million of compute hardware that they bought, right? This is just on one purchase. So when you do that, who's warranty? One of the key things they want to know is who's the manufacturer going to cover that warranty? If we, you, I touch that, and they say, time out, we didn't approve that. That's our number one thing right off the bat. Other questions? Yes?
Yeah, I have a forced air fueling right now, and I'm thinking about going to a chiller. But I'm wondering where I can go to really get an honest opinion. Do I keep forced air or do I just...
You know what? You can go to your local guy and get a CFD. It's called a computational fluid. Yeah, that should tell you honestly right there. And then not for a specific manufacturer. There's multiple manufacturers that can meet that cost comparison. So you can go to a local consultant in your area. Where are you?
East of San Diego, about 100 miles.
Okay. So there's local firms. As a matter of fact, John Parker, who's got more money than God, he lives out there in Southern California. He's part of AFCOM. He could probably tell you a couple consultants down in that area that will give you an unbiased view.
The difference is I'm in the desert. It's 115 degrees all summer long.
Yep. Well, there are going to be some issues but you know what? The good part about doing an engineering, a feasibility study like that, it's objective. It's going to tell you what the numbers are. There's no BS. That's it. Here's your return on investment. Here's your not return. We've done energy conservation measure studies that say, if you do this, it's going to cost you $5 million and your payback is 72 years. They said, go jump in the lake. We're not doing anything 72 years. But on the other side of it, we've done things where we said, you invest $3 million. Your payback is in 18 months. They said, sign up. Other questions as we wrap this up? Because otherwise we could turn the heat up and just keep on going. We got another 4 minutes. Any other questions that come to mind? You want any investment advice? I can tell you where to put your money. No, I'm only kidding. Any other questions? Well, listen, if there's no other questions, thank you for your time. And fill out the surveys. And if you have any questions, I will give you, you can send me an email and I'll respond to you. But thank you and have a great session. Take care.